sure this pen is working the way it needs to. I'm gonna go with yeah. And do that again. Alright, what is this? Just doing a quick volume check here, I guess, as I'm just trying to chow through some emails on my phone as well. This doesn't look right. Does it? Oh no, that does. Okay. Oh my goodness. 60 seconds. Oh, I totally need to read that. Okay. Could have sworn there should have been one more of these. Oh yeah, there's two right there. Okay, 26. There it is. Okay. Yep. Check the date. 10, 9, 8, 7. Let's put that away for now then. 3, 2, 1. And yeah, all right, welcome back. Just a quick round of announcements. Today is Tuesday, April 14th. Quiz today. Again, though, these are always like, I would just do it today. It's available already. But turn it in by the end of the day tomorrow. Just recognizing people's schedules are a little different than in the past. Just like the quiz last week, please turn it into not into Canvas, but instead into Gradescope. Yeah, just thanks for kind of rolling with the punches as far as that change goes. As is usual, a response is due Wednesday, a homework is due Thursday. Please start, if you have not started already, please do so. I think sometimes what happens is there's during the office hours on Thursday is a time when people come with like 3 out of the 5 questions that they're like, I don't know where to start. That's not really the timing I would suggest. A homework will always be posted by Thursday morning for next Thursday, so please think about starting early. And then this one's new. I just posted this about 2 hours ago, but there is an ungraded quiz that's in Canvas that I would really appreciate if everybody would give a try. It's called Mid-April Survey because it is the 14th of the month. I meant to get this out sooner, but I've been trying to figure out how to import things for grading, and I'm behind in kind of a number of ways. And in any case, I was like, I had little pockets of time between classes today. I'm like, I just got to get this out. So this survey is, if things are going great, cool, you can write about that, but this is really just trying to find out from you all like what's working, what's not working, and if you don't fill it out, I'm just going to assume everything is fine. If there's anything that's not working, though, even if it's small, I would really, really appreciate that you just take a moment to fill it out no matter what, so I can see are there any common themes, like things that a lot of people are having trouble with, so that if there's a way to change that, great. I probably can't fix every single little thing. Any change of any kind, like testing things out, is going to take up time. But like if a lot of people are having the same struggle, I would like to do what I can to fix it. So I need some kind of feedback related to that. Today again is not to introduce anything that's technically new, but I do want to kind of preview some of the big ideas for what we do starting tomorrow. So tomorrow we look at cardinality. It builds completely off of functions. You got to have this stuff down in order to make what we're going to do next make sense. So you're going to hear a bit of repetition, and I apologize for that. But the things I'm repeating are with good reason, because these are the things that people tend to make mistakes on. So I want to try to prevent those mistakes by saying you should think this way instead of that way. That's what today's about. So one of these things you've heard me say quite a bit about, I hope, is there's a difference between f versus f of x. So f is a function. F is the name of the function. I mean, a function is a special kind of relation, which is a special kind of set. Whereas this, f of x, assuming, okay, the detail of x belongs to the domain of the function, then this here, f of x, this should be an element of the codomain. And so there is I'm going to try to say kind of a couple things. So if the order is different, this should still work out. So when we covered everything last week, I had to be very, very careful with the order of things because we had to introduce one thing and then the next and so on. Now that we have all the things as of last Thursday, even yesterday, you might have noticed there was a little jumping around. Same deal today. I want to clarify a comment from last week. So to fully define a function, you have to say, you must state the domain, the codomain, and the rule. Right? There are three things that need to be specified. And there's a comment I want to make related to this in just a moment. So first of all, another thing I'd like to recall, sorry if this is a little jumpy here, two functions, f and g, let's name them, are equal. And we write f equals g if they have the same domain. They is my pronoun here for f and g, of course. So if they have the same domain, and let's just name it, in this case, capital D, have the same codomain. I don't even need to name the codomain here. I could have used a capital C or something, and same rule. And same rule. And what we mean by same rule is for all x, I guess, in the domain. That's the only reason I wanted to name it capital D just a moment ago. We have this property that f of x is equal to g of x. So among the things I guess I want to do right now is just point out that this f equals g, you see both for the f and for the g, this business of those are function names, versus over here, f of x, g of x, that's this type of notation thing going on. The other thing I want to do is I want to follow up on this note here, because there's something about it that might seem a little confusing, and this note, I think this is a note to follow the note. This note will make more sense as you start looking at the homework that's due Thursday, and as you look at some things that are upcoming in the next section. So I just want to comment that there are times. So yeah, to fully define a function, you state domain, codomain, rule. However, sometimes this is the kind of thing that happens. So there are times when you define one function's rule in terms of another. We're going to see quite a lot of this tomorrow, the next day, and the next week on Monday as well. So let me try to give an example of what I mean by this. Right? So you might see this kind of situation, like I might type to you, like in a homework question, something like, let f, let's just say, be a function from integers to integers. Be a function. So I might, so you'll notice even right here, this is not fully defining a function. Out of the three things here, the domain, codomain are provided, but the rule is missing. And sometimes an exercise intentionally does not include a rule because the thing that you need to prove should apply to any function with domain z and codomain z, no matter what rule. So, or same thing in stating a certain theorem that would need to be proved. Maybe it's a theorem that should apply to any function where the domain is integers and the codomain is integers. So, yeah, this is not a fully defined function because the rule is missing in this sentence, but maybe it's just enough information anyway to complete the problem. So you might have a situation where that occurs, like that's what I've told you, and then you might need to do the step of writing a sentence, it depends on the problem, that might look like this. So you might need to write something like define the function, and to use a new letter because f was already used, you might end up needing to define a function, let's say g, with domain, codomain, well, you specify, by, and then here, so you've already, if you write from z to z, you've already given two out of the three things necessary. But you might provide the rule like this. You might write g of x equals 3 times f of 2x minus a 7. Now, where did this come from? I just made up a thing, okay? But what I'm trying to say is, even if in my line here I did not provide what specific rule f was, here, let me use a new color, in red, you're still referencing it anyway. I hope that makes sense what I mean. I don't want to dig into this too long. Like, so just as a comment, the idea here being like, based on how g is defined in the sentence, then g of, I'm just going to make up a number here, g of 10 would be 3 times f of, well, 2 times 10, so 20, right, minus 7. So then f of 20 is computed using whatever the rule for f was, even though it wasn't specified, and then that resulting integer would get multiplied by 3, and then you subtract 7. So sometimes things like this happen, even if the problem doesn't state a function fully, because only 2 out of the 3 parts are given. It's just enough to maybe complete the problem anyway. So one rule, like the rule for g here, is defined in terms of the rule for f. So you're sort of piggybacking off of things like this. Okay. And then the key thing we did yesterday, and I see it in my notes one way, but I'm going to write it slightly differently right now. It's basically all the same, but I'd like to just say if you have a function, you're told you've got a function f from x to y, just, range of f, this should be, here's how I think about it. It's you go through each element of the domain, and then you apply f to that element s, right? On the other hand, if you had, I'm going to switch up the order even. So let's say you had a subset of the domain, so maybe a capital S that's a subset of the domain, then the image of that set should look super similar to what we just had over here. It should be all the f of s's, but not for every little s. Now it should just be those s's that belong to capital S. And we drew a cartoon kind of sort of Venn diagram version of this yesterday, but I want you to stare at this and even, I don't want you to memorize symbol by symbol or word for word. I want you to go, okay, f of capital S. It's like, well, apply f to each thing that's an S, and then gather all those things together in a set. That's what this over here is trying to communicate, right? And then I guess maybe this comment should have come earlier. I just wanted these two items to be right next to each other right now. If you had an element of the domain, then of course f of it should be an element in the codomain. And then here's where I'm going to change up things from yesterday. Now, yesterday I used capital Z and lowercase c because I wanted those corresponding things to show up nicely in the cartoon Venn diagram thingy. But right now, I'm going to do it this way. So if you've got star, that is an element of the codomain versus a subset of the codomain. Of course, these are different things, right? You either have one thingy in the bag that's star in capital Y versus star subset of capital Y, meaning you've got over here, the second star is a set, right? So everything in this element, or every element of this set star would be an element in Y. So these two already start differently, but I'm just trying to get at, you've got preimage of just an element of the codomain, and you have preimage of a subset of the codomain. I guess this one's easier, but we should collect together all the, I mean, think of the cartoon again. It's just, this is asking what inputs lead to the output being star. So, I mean, think about how, if it's inputs, I guess you could put an x here, or whatever placeholder variable you want. Those inputs naturally have to belong to the domain, and we just need to satisfy the property that f of that input needs to equal that thingy star that was provided, right? I see people doing all kinds of just made up things of like putting like f of star equals x or all kind. I mean, you want to think what's an input, what's an output, and I mean there's to the -1 this pre-image symbol right here to the -1, so that should help clarify. You know, I want you to sort of think in terms of the cartoon we drew yesterday, and it should help recreate this set as written right here. For the next one, it's just a slightly more complicated version of this. You'll notice that you want to, you know, just do this, but you can't because star is not an element now. Star is a set, right? So we've got to be more careful, and we need to talk about something belonging to that set. So let's use a new letter. I don't know, like a B. B in the set, right? So think about it. If, I mean, this is a set just because it's a subset of Y. So now we've got B in that set, but if you have B in star, and star is a subset of Y, and Y was a codomain, then think about what little b is. Here, little b is not an input, it's an output. So if little b is an output, think about where it ends up. It should be f of something equals b, right? So, yeah. So, and then we need something to fill in this spot right there, right? So that would be the, well, that's an input. So maybe we'll call it x. So we should only keep those x's that satisfy this, but now we need a quantifier because this b should be some kind of placeholder variable. And think about, the whole point here is just to like really process what for all means and what there exists means, to think about which thing it is. Should it be that f of x is equal to each thing in the set star? That wouldn't make sense. That would sort of, in a sense, informally speaking, mean that the function doesn't pass the vertical line test. So this really ought to be a there exists such that here. Okay, the key thing here being that both of these, just with how they're defined, these are both subsets of the domain. Okay. And again, I don't think it's worth memorizing these, right? Understand, think as intuitively based on what we did yesterday for what these really mean. So understand intuitively. Think of the picture. I want you to memorize the picture, right? Process what these things are trying to say each time, and that will then lead to, this leads to these definitions over here. And like the exercise yesterday that we did where you had, we did it sort of, there was the sort of in class with an early function that I presented first, and then there was a worksheet at the end. Like, I guess I made those exercises, but you could have done that too, right? Like, what I'm trying to do is model this idea that every time, I remember being a student in courses of this kind, where every time you see a new definition, right when you first learn a new definition, it seems difficult. But to get comfortable with a definition, yeah, of course, struggling through homework is an important part of that process, but one of the warm-ups you can always do before just diving into homework is go, wait, what is this definition saying? And make examples yourself that help go, okay, you can build intuition for, this is a set, what kind of creatures live in the set, right? So you've heard me say this all semester already of like, if you have a set, the next thing to do is ask yourself, what kind of things belong to the set? Well, for instance, over here, I'm using this fancy language of both are subsets of the domain, but I could have said these are both sets of, well, I don't want to say integers, but sets of x things, right? Like the things that belong to capital X. So it's the same thing that I'm trying to ask you to have a habit on all semester of you have a set, what belongs to it. That I'm just using the fancy language for it. They're both subsets of the domain. So just as a brief version of this, so let's take a function I'm fully defining for you. Domain is -10 to 10, so all reals between -10 and 10. The codomain is the set of all reals. The rule is a very familiar one to you, f of x equals x squared. So we'll talk about this here. Okay, so this, by the way, is not inverse function, right? So this is not inverse function. That's not what's going on here. You can't talk about inverse function, in fact, because if you were to graph this thing, you'll see that the horizontal line test fails. So this function is not injective. For that matter, if you take a look at the codomain being the set of all reals, this function is not surjective either, right? So not injective, not surjective, so definitely not bijective, because bijective required both of these properties. So this is not the way to read this. If you read this as inverse function, or you say f inverse of 36, you're making the mistake that I tried to spend essentially all class yesterday talking about, right? We spent 55 minutes where that was really the focus, and I want you to stare at this and say to yourself, we've got to apply the definition of preimage. Right, it's this one, by the way, because that's why I wanted to use a star in both of these. Maybe I'll circle these in red over here. I wanted to use a star in both of these places because you see f to the -1, and then in parentheses you see star. You should always ask yourself, what is that star? Is it an element of the codomain, or is it a subset of the codomain? In this case, 36 is what's the star there, and that is an element of the codomain. So we should be. You can look at the direct definition up here, or think about how we processed this yesterday, right? So because we work through what this means, right? Because I've internalized what this means, we should be thinking about what inputs give 36 as an output. What inputs lead to 36? What inputs, if any? Because there could be one, there could be more than one, there could be none. Anything is possible. If there's none, then the final answer would be empty set. In this case, though, so you always get a set, even if that set is the empty set. Don't say this is undefined. You always get a set. The empty set is a set. It's not a set. The empty set is a set. In this case, we end up with a set consisting of two elements, right? +6 and -6. If you look at, as another example, preimage of the set 36, 37, 38, now we need the other definition. So now star, I'll underline it in red again, right there, is not an element of the codomain. It is a subset of the codomain. Right, this 3-element set is a subset of the codomain. Again, because I've internalized what this means, I look at this, and you can go back to the original definition. That's always a good thing to do, but I'm asking what inputs have an output in the set 36, 37, 38. That's all that's being asked here right now, right? So you can work this out here, that just in the interest of time, I'm going to write this up here, that we should have 6, -6, root 37, and then -root 37, and root 38, and -root 38. So here we get in this case, the preimages again. So just like up here, maybe I'll circle these both in blue, that and that. These are both subsets of the domain. So this is a good place to pause, make sure we're doing okay. See if there's any questions, comments. Okay, so then I'd also like to review a little more. I mean, it's all a bit review today. So let's have a function f from D to C. I happen to really like using D and C because, domain, codomain. but that's just a little bit of a preference. It's been a while, so just a reminder that F is injective, or you could use the phrase one-to-one. I think some books put like dashes in between. I don't really care whether you do or not, but the key thing is, the good part is, what does this really translate into? And this is for all two things in the domain. Oh, I have an error in my notes. It should be domain. Okay, for all two things in the domain, if they have the same output, so if f of x equals f of y, then x is equal to y. Maybe you're bothered that I'm using little x and little y both to be inputs, but okay. So if you don't like that, maybe switch it from x and y's to m's and n's or whatever you'd like to do. F is surjective or onto. Either word works. They are both adjectives if the following happens. So for each thing in the codomain, so maybe I'll use a C here. Yeah, for all C in the codomain, there exists a thing in the domain, so there exists D and D, such that f of D is equal to C. And then finally, F is bijective, or this awkward phrase is a one-to-one correspondence if both things happen, right? So both of these things above have to happen. Now, here's another thing that I just need to talk about, is that sometimes people get in this strange habit around this time of the semester where they're like, hey, in homework you asked us to prove that this thing is surjective or this thing is injective, and we never saw a thing like that in class. And we will in a moment anyway, but I think the bigger story here is that's not the game we're playing at this point in the semester anymore. We've dealt with definitions. We know that the first if that you read is an if and only if. So meaning this text right there is the same as this text to me, right? You already saw this apply when dealing with relations. Like at some point you had to prove a relation was symmetric. At another point, you had to use that a relation was symmetric. I had people in office hours talking about these things. The first time around, I get it. But the point is now, if you need to prove, like, I want you to always process definitions in this way. Like, I don't want to, I mean, if we need to, we will state this over and over and over and over again. But the point is, there's always now, every week with definitions, they're always using the same grammar going back from the very beginning of the semester, ands and ors and if-thens and if and only ifs and for alls and there exists. So always using that language. It's always predictable that the language is always one of those phrases or a mix of those phrases. And then the point is, if you need to prove that f is injective, then you need to prove what's in this blue box over here. Right? So if you need to prove what's in that blue box, you should then ask yourself, usual question, it starts with a double for all. So how do I prove a double for all? I got to have something arbitrary in D and then have a second thing arbitrary in D, right? So you don't at the beginning assume those two things picked from D are the same or not. There's just that process and follow it. On the other hand, in a different exercise, you might need to use that a function f is injective. Then you need to use this for all statement over here, right? So then think about, how do you use a for all x and d, for all y and d? You got to have two specific things in capital D. And if you don't have two things in capital D yet, then wait to use it. Don't switch to trying to prove it. If you know you have to use the statement, maybe by working on another part of the proof, eventually you get two elements of capital D. Right? So it's the point is, I want this to be no surprise. And if we go back to there was that time we were looking at chapter 3 section 1 called methods of proof, and we spent 10 days on that section, and I said those are the most important 10 days of class. I cannot stress that enough. Nothing that I am really doing at this point is anything all that I want to say interesting from the standpoint of you could in principle be doing this on your own. Like, we've modeled everything there is to model. I want to say that every time you see a new definition, it just uses that old grammatical language. Yeah, sure, it's different each time. So what I do in class is I try to now provide examples that you could have come up with in principle that help to illustrate kind of what are the funky things that can go on in a specific definition. But as far as proving whether f is injective or surjective, I want to say you've got those tools, right? So remember that you have those tools, and just be I'm not trying to rant, I'm just trying to let you know that you are empowered to do these things. We've talked about proving and using for alls, proving and using there exists. You're going to see that over and over and over. And in office hours, I expect people to get stuck. Don't get me wrong. So I don't want anybody to be like, oh, no, I can't ask this in office hours. You definitely should. But a lot of the times, one of the things I think that I can do to help make it so that you start seeing this on your own for the next week or the week after is I try to ask questions that are very generic, not because I'm trying to be unhelpful, but because I'm trying to ask questions that can be asked the next week and the week after. So you'll very often hear me say, I confirm to you that you are correct, that yes, you need to use this for all statement. How are we going to use this for all? What else do we need? I ask questions like that all the time. Okay, during office hours. So, and then just as a comment, right? So we shouldn't say things like f of a is surjective. You know that's not good language because the adjective here is being applied to an element of the codomain. Instead, the language to use is f is surjective, and of course, same deal for injective and all that business. We saw just this bit of review of you've got a function, let's say from a to b, that is bijective. Then the inverse is a function where you swap the domain and codomain with rule written as a set anyway. It is if you had an ordered pair. So as you run through the set f, if you had an ordered pair xy, then in f inverse you have the ordered pair yx, right? And this idea will come up and I'm going to remind you of a thing you did way back in an algebra class. And another way to interpret what's going on here is to say if you have f of x is equal to y, which is what that thing is saying, right? As you run through any ordered pair that looks like that, then in f inverse what you have is f inverse of y is equal to x. And the key warning, I mean the thing that you've already heard once today and kind of almost all of yesterday, is that the inverse function is only defined if f is bijective. So sorry if it sounds like I'm so paranoid about this, but I can't tell you how many times people are looking at a question, and because it's typed a certain way, they look at this kind of notation right there and already start saying inverse. I'm like, wait, do you know if it's bijective or not? And they'll, so I get it. Old habits are very hard to break. I know that this notation is like, you're thinking of things like this, sine inverse. I get it. But you gotta be really just very literal with the definitions. And so if you see f -1 power, I'm really myself just trying not to use the word inverse unless it's appropriate, of something, let's call it squiggle, you need to ask yourself the following question. To help sort things out, this is where I think yesterday's question about does context help somewhat, I think is the answer you heard yesterday. So I want to clarify, if that squiggle spot is if squiggle is a subset of the codomain, then there's only one way to interpret. Then you have to apply the definition of preimage. It's the only option if you have a subset of the codomain in this spot right there. So you have to then interpret this as all the things in the domain. Oh, I should have maybe let's just call this f from x to y, right? Then this has to be all the things in the domain which satisfy the property that there exists a thing in this set such that f of x is equal to y. It's the only option. Even if f is known to be bijective, if this spot right there is filled with a subset of the codomain, this is the only option. Now, if, on the other hand, if the squiggle is an element of the codomain, then you've got two options. Maybe. You have at least one option for sure. So let's say you were told, I was told, or can prove that f is bijective. So maybe in the homework question you are told f is bijective. Or even though you weren't told it, you could, based on being given the domain, codomain, and rule, you could yourself prove that the function is bijective. If so, then how do you interpret this? Now you have two options. Option one is apply the definition of preimage. So using yesterday's notation, I mean like that, right? And what you're going to end up getting when you do so is you get a subset of the domain of the original function. So you get, what you end up with, just to comment on it, is you get a subset of x. That is one option. Your other option is to look at an output of the function. Look at an output of the function f inverse, which, by the way, you've got to swap the x and y from up there. So we're going to go from y to x. And when you do that, so f inverse, I am now using the correct word, applied to an element y. So let's still call it c here maybe. But anyway, this squiggle spot, maybe I should have just used a squiggle here as well. This squiggle, by the way, we said already up here was an element of the codomain y. So then this ends up being an element of x. So you'll notice whether you use option 1 or option 2, you either get a subset of x or you get an element of x. And both are correct answers, even though they are different from each other. Is the arrow something we can, question came up, sorry. Is the arrow something we can conclude or an additional piece of information? I'm just trying to sort of state that if you know that your function f is bijective, then you've got two ways of interpreting this thingy up here. And you are allowed to use either interpretation, even though the two interpretations give you technically different answers, because one is going to give you a set and the other is going to give you an element. Both are technically allowed. It turns out to be the case that the set that you get in the first case ends up being a singleton. So information-wise, it has the same info because it's either an element or you get that same element wrapped inside curly braces. But the point is you always, in this case, have your two options and you get your choice. On the other hand, if you know, so the other option is maybe you have a function, I know f is not bijective. Again, either because you were told specifically in the problem, or you proved that f is not bijective, or here's the other key thing, or I'm unsure. Maybe you're in this situation, I'm unsure if f is bijective or not. Like maybe you just don't have enough info. So then if you don't have enough info to know whether f is bijective or not, don't assume that it is. The point is, in either of the situations, you either know f is not bijective, or maybe f is bijective, but you don't have enough information to know for sure, then you only have option 1 from over here. There's only one option, right? Then you have to apply the definition of preimage. It is the only option. And you get a subset of x. So this is, I'm just copying the same box as over there. Do you get what I mean? Is that this option 2, the big error that people make is assuming that they have this second option over here. You never have this option if you don't know that f is bijective. Okay. Again, sorry to overdo it, but like you really, like this is one of the, I know it's a confusing thing. It's really unfortunate how the notation looks. There are books in the area that intentionally use I'll just point to it here, like different notation there versus yeah, there, yeah, actually, right? But most books don't use different notation. Most math books that I've ever seen use this clash of notation, this inconsistency of notation for these two different things. And since most books expect you to sort this out, I'm expecting you to sort this out too. We're going to just deal with this difficult thing, is what I'm trying to get at. I want you to experience some of what's going on here. And so I want to say it this way, and I know that we've already looked at maybe some of these ideas, but they may be a little jarring. So if you had a function f from r to r with the rule f of x is equal to sine of x, okay, this is not bijective. Remember, bijective required injective and surjective. This is neither injective nor surjective. It failed on both counts, right? So there's no inverse function. No inverse function. When I teach pre-calc, I talk about sine having an inverse function. If I am in the learning center and I'm helping somebody with their Math 151 or their Calc 207 stuff, I say inverse sine function and so on and so forth. But not in this class, not in 225, not in any class after 225. To use a new function name, if you had negative pi over 2 to pi over 2, closed interval, and then the codomain was negative 1 to 1. So with rule g of theta, I switched the x to theta just for funsies. Sine of theta, this is bijective. Okay, so g has an inverse. There is an inverse function. So in fact, g inverse, where you have to swap the domain and codomain, looks like this, right, for the domain and codomain issue. And then here's the rule. With rule, g inverse of y is arcsine of y. Okay, so there's those two kind of examples that pair together, right? You have this non-bijective function f, and you fix it by kind of cutting off a lot of the domain. You basically cut off just enough so that the periodicity issue is completely gone, and then you cut off the codomain just enough so that every codomain thing really was achieved as an output, because sine's values are always stuck between negative 1 and 1. Same deal with cosine. So I'm going to have a pair of examples. New function name, k. So the usual one that's introduced in a trig or pre-calc class is a function, let's say, called h, actually. So h of x equals cosine of x. This is not bijective. So there's no inverse function. So there does not exist an inverse function. That's not what I tell a pre-calc student or a student studying trigonometry, but you're getting the real scoop here. And so we got to fix this to create something that is bijective. For cosine, because it's the x-coordinate of the unit circle, you got to change the angles you consider. Instead of negative pi over 2 to pi over 2, since cosine is the x-coordinate of the unit circle, to get all the values once and only once, we're going to only consider angles between 0 and pi radians, and outputs negative 1 to 1. So with the rule here, k of theta is equal to cosine of theta, this is bijective. So the inverse function is k inverse has, of course, swapped the domain and codomain. So negative 1 to 1, and then codomain 0 to pi. And the rule is k inverse of x is equal to arc cosine of x. Also, you may have seen the notation as cosine inverse of x. For the next pair of examples, hope we're doing all right. Okay, for the next pair of examples, I'd like to look at, first of all, it'll be convenient to define a set D first. So it's going to be the set of all reals, set minus pi over 2 plus pi n as n runs through the set of integers. So I'm trying to remove the angle pi over 2 and then every pi radians after that. So if you have a function I'll call little p from d to the set of all reals with rule p of theta is equal to tangent of theta, this is not bijective. First of all, I had to set up the domain sort of strange here to make sure that everything in capital D has an output. Right? So that's why I defined the set D first, because it was kind of a bit of a mess. So P has no inverse. Okay. Actually, this function P, it is surjective. So every real number ends up being an output of tangent. But the problem is tangent is periodic. You've got all these strands. And so we only want one of those strands. And so the way to solve this issue is to create a function Q using the same, not using the same D over there. We've got to cut off most of it. So we'll only look at one strand. So from pi over 2 to negative pi over 2 to pi over 2. With rule Q of theta is equal to tangent of theta. So this is bijective. This function Q is bijective. And so Q inverse, defined from reals to the open interval negative pi over 2 to positive pi over 2, with rule Q inverse of M is equal to arc tangent of M. Okay. And then just one more pair of examples. So let's look at the function little r from reals to reals with the rule r of x is equal to e to the x. This is not surjective. Okay, it is injective. You know, look at the graph of the exponential function. There's no horizontal line test failure issue, but it's not surjective, so not bijective. Okay, so no inverse. If you want an inverse, good thing the horizontal line test issue is already fine. So injective is good, but surjective didn't work. We just need to fix the surjectivity problem. And the way to do that is really just to include only the appropriate real numbers. So just the set of positive real numbers, everything bigger than 0, right? That would end up being the range anyway. So we'll shorten down, we'll shrink the codomain to just have the appropriate set here. So I'm naming this function s. Yeah, s of x will be e to the x. So this is bijective, right? I mean, to make it clear what is bijective, maybe I should do this. S is bijective, just to be a little grammatically good right now. And so there is an inverse function. The inverse function, you got to swap the domain and codomain. This inverse function, I could use an x again. Why not? It is just a placeholder variable. This inverse function, it happens to be log base e of x. Okay, there's one last. Are we doing okay with those collections of examples actually before moving on? Any questions, comments, what ifs, anything like that related to? I'll scroll back up just to make sure and see if anybody's got a question. It's kind of different, huh? Right? Just like it's a strange thing of, I took a pre-calc class and learned about sine inverse and cosine inverse, and yeah, those have their place, but like because of the periodicity, like maybe you can even think back, or even if you look at a pre-calc book, or once we meet up again at some point all in person, just drop by my office, look at a pre-calc book on my shelf, just say I want to look at it for 10 minutes, and you'll see authors of these books trying their best to try to dance around this issue and talk about, well, you can't just flip the picture diagonally along the line y equals x and hope to have something that passes the vertical line test, but you've got to cut things. And that's why things like arc cosine always gives you an angle that's between 0 and pi radians. That's why arc sine always gives you an angle between negative pi over 2 and pi over 2. If sometimes people try to provide an arc sine output that's outside of that interval, and it's technically incorrect. So I mean, there's a lot of kind of funky things that are actually, to be honest, truly related to doing things like teaching a high school math curriculum that come up in this process. What I do want to do is this little bit of a promise that I had. So I'm going to let's do this. I'm going to define capital D to be the same set as capital C to be the set of all reals. I'm doing even I could have just used R in both places in the next sentence here. So I've got, but I intentionally am using a capital D and a capital C because I think it looks confusing otherwise, and I want to make sure when we have quantifications in D and quantifications in C, it is crystal clear which one and why based on the definitions that we have. So I'm going to define this function f from D to C. Let this function have rule f of x is equal to 3x plus 4. So there, domain, codomain, rule, functions completely defined for you here. So I'd like to prove to you that f is bijective. So proof, we have to prove f is injective, we have to prove f is surjective. So if you go back to the definition to prove f is injective, I hope it's okay that I just scroll up to do this way back over here. Proving f is injective. Oh, it's in the blue box. The thing you're proving starts with 2 for alls. So I don't want this to be a I don't know how to prove something is injective. No, it's always going to be like, look at what the definition is saying. It's 2 for alls. You got to have 2 things in the domain. So they're called x and y up there, but I'm gonna stick to my notes and I'll just let u and w in domain. Okay, be arbitrary. You could write the words be arbitrary if you want. Now, I won't keep scrolling back up, but we need to prove an if-then. So we have to suppose that f of u equals f of w. So, and then we need to show the conclusion of that implication is u is equal to w. Again, here, it's not about, I know this is new, so you may be like, where did all this come from? But the key thing to think about is injective is trying to say no matter which 2 things from the domain you're looking at, if the outputs are the same, the inputs are the same. You want to use that language as opposed to trying to memorize injective kind of symbol for symbol and word for word. So we start with this information, f of u equals f of w, and we eventually want to get to u is equal to w. Now, since f of u equals f of w, we get, now, I'm not doing something to both sides, I'm just simplifying each side differently. First of all, the left side says f of u. And if you look at the rule, f of a thing is 3 times that thing plus 4. So we have 3u plus 4, right? F of u, I think not a lot is happening, but if you miss this, then I just replaced the green thing underlined f of u with 3u plus 4. Now we can replace the blue underlined f of w with 3w plus 4. Okay, all that happened was each side independently. The left side was replaced and the right side was replaced based on the rule that I'm underlining over there in black. That's all that happened here. Okay, so we get this. So subtracting 4 on both sides, we have 3u is equal to 3w. So dividing both sides by 3, we have u is equal to w. Cool, that's what we wanted to show right there. So we have right now a rather short but complete proof that f is injective. Now we should prove that f is surjective. So new paragraph to prove f is surjective. The definition of surjective had started with a for all blah in the codomain. So how do you prove a for all? That's what the game is here. So we pick an arbitrary, we let the reader pick an arbitrary thing in the codomain. So I'm going to call that thing y, just as a reminder that it's an output. And we want to show now there exists x and d such that f of x is equal to y. So this is what we want to show. And how do we show a there exists statement? Somebody want to unmute or type? How do we prove a there exists statement? Right, going way back to the big 10 days from the 3rd and 4th week of the semester. How do I prove a there exists statement? Okay, we've got to define a thing. Yeah, define an appropriate element. That has to end up being in capital D. Thank you, Rafi. And then prove that the conditions are satisfied. So we'll do that. I'm going to write let x equal fraction y minus 4 over 3. Question, can I do this? Can I write let x equal, well, yeah, because let should always be followed by a new variable that hasn't been used yet. This doesn't count over there because it's a placeholder variable in a want to show statement anyway. But does this end up defining x? Yeah, it ends up being x is whatever y was over here, subtract 4, then take the result, divide by 3. You might say, where the hell did you get this? I'm not addressing that issue right now. I will in just a moment. Okay, but first of all, then if x is defined as this fraction, then x belongs to D, right? D, by the way, was the set of all reals. So if you start with y, a real number, y was in C, so y is a real. You take a real number, you subtract 4, and you divide by 3. There's no like divide by 0 kind of errors or anything like this. Yeah, sure, that number is in capital D. And then more importantly, we still need to prove the condition that f of x is equal to y. So take a look. And f of x equals f of, well, x was y minus 4 over 3. So just replace it. And then if you apply f, based on the rule, up here, I'll box it. 3 times, replace y minus 4 over 3 plus 4. Now we'll simplify, cancel the 3's. You have y minus 4 plus 4. Cancel the minus plus 4's and you end up with y. So cool, we've got f of x equals y, which ends up proving this. So that's the proof, right? We've proved injective, we've proved surjective. I've got one last thing for y'all, because I anticipate the question, where did you get this fraction? So the last thing I want to do is I actually want to address what is the rule for, so now that we have a bijective function, we just proved f is bijective, so we know there's an inverse function where you switch the domain and codomain. So what is the rule, right? I've switched the D and C, D arrow C is now C arrow D. And here the answer is you got to go back to your algebra days. So what's going on here is we want to find an x such that f of x is equal to y, right? So this is what inverse is about, right? Like if you want to know what's the rule for f inverse of y, remember we've got this property that f of x is equal to y. So the roles of x's and y's swap, and we're just trying to figure out what should belong here, but then you can replace the f of x with 3x plus 4. And then since we want to find what x is, let's solve for x here. So you subtract 4 on both sides. 3x is equal to y minus 4, and then x is equal to y minus 4 over 3. So it turns out that the rule for f inverse, if you call the input to f inverse a y, is y minus 4 over 3. So that's where this came from here. Okay, I'm out of time. I'm actually a minute over. I apologize. So questions? Otherwise, we'll call it a day.